Hello everyone, this is tutorial number 3, Fundamentals of Data Converters. My name is Yun Chu and I'm with the University of Texas at Dallas, and today I will be the speaker of this tutorial. Here's the outline of this tutorial. We will start off with basic concepts of quantization and sampling and a quick overview of data converter architectures, followed by performance measurement techniques in both time domain and frequency domain. I will then cover Nyquist rate ADC and DAC architectures in some detail and circuit building blocks, including comparators and sample and hold circuits. After that, we will also examine a critical concept in analog to digital converters, the redundancy, and how we can exploit redundancy for digital calibration. Toward the end of the tutorial, I will cover the figure of merits of ADCs and highlight a few interesting papers received this year at the ISSCC conference. Everyone knows that data converters serve a critical need in microelectronics. They are the components responsible for converting back and forth between continuous time, continuous amplitude analog signals and discrete time, discrete amplitude digital signals. If we look inside these converter boxes, in general, there are three key functions involved: filtering, sampling, and quantization. Now, filtering is actually still an analog operation, but sampling and quantization would be unique to data converters. In the analog to digital converter case, usually you start off with anti-aliasing filter such that signals do not overlap in the spectral domain after sampling. And finally, you quantize the signal. In the digital to analog converter case, the whole process is reversed. Now let's start with quantization. There's a simple way to understand quantization in data converters. In the analog to digital converter case, it is related to division. In the digital to analog conversion case, it is related to multiplication. Suppose we have n number of bits, a full-scale signal range, VFS, which is set by the reference voltage, Vref, supplied to the converter. We also define the least significant bit size, delta, as VFS divided by 2 to the nth power. Now in the ADC case, the digital output Dout is equal to the input voltage divided by the full-scale range, then normalized to n-bit word, which is equivalent to divide the input by the LSB size. In the DAC case, the output analog voltage Vout is equal to a summation of all the bits weighted by or multiplied by a geometric series in delta. That's why it's multiplication. You probably noticed the truncation of floor symbol in the division case. That means every time we perform quantization, we're subject to truncation errors or quantization error. This is illustrated in this diagram where a 3-bit ADC transfer curve is shown in blue. The quantization steps are ideally uniform, resembling a staircase. Now let's fit a straight line through the staircase, and the difference between the two, which is plotted in the zigzag waveform, is the quantization error. The errors are ideally bounded between plus minus delta over 2 or half LSB size in the ideal case. In the case when n is large, so the LSB size is small, the input is also large and busy, then the quantization error can be considered uniformly distributed with a wide spectrum, similar to white noise. It is therefore often called the quantization noise. With all these assumptions, the quantization noise can be calculated to have a power of delta squared over 12. Since quantization error is considered as noise, we can then define a signal-to-noise ratio of the converter, or more precisely, signal-to-quantization noise ratio as QNR. For sinusoidal input with a peak-to-peak swing of VFS, the SQNR can be calculated to be 1.5 times 2 to the power of 2n, or in dB, 6.02 times the number of bits plus 1.76 dB. This table maps a converter resolution to its ideal SQNR. For example, a 12-bit converter has an SQNR of 74 dB. I have to emphasize that SQNR only reveals the theoretical performance of an ideal quantizer. In practice, there are many other types of performance impairments in a converter, such as electronic noise and signal distortions. In the case of an ADC, there is also a potentially catastrophic error called metastability, in which the comparator simply fails to resolve within a given time limit. Now let's look at sampling. Suppose we have a continuous time signal x of t, which has a spectrum xj capital omega, sampled periodically every t seconds to produce a discrete time sequence x of n, which has a spectrum xj little omega. Here the sample rate is fs equals 1 over t. Now the question is, what is the relationship between the two spectra? Since the sequence x of n can be obtained by multiplying the original continuous time waveform by a train of impulse functions, the discrete time spectrum then can be calculated by convolving the continuous time spectrum with the spectrum of the impulse train, which simply replicates the continuous time spectrum indefinitely, uniformly spaced by omega s, as shown here. To avoid any overlap of the replicated spectra, or a problem called aliasing, the minimum sample rate must be at least twice the single-side bandwidth of x of t. This is called the Nyquist rate sampling. Next, let's take a quick overview of the ADC and DAC architectures. For ADCs, we usually categorize the architectures according to how fast a conversion output can be produced. In the slowest case, we have the integration ADC, in which one conversion level is produced in one step. Therefore, it needs 2 to the power of n conversion steps to finish converting a sample. On the contrary, the flash ADC is the fastest and converts a sample in one step. In between these two extremes are the successive approximation and pipeline ADCs. In the SAR case, one bit is produced in one step, while in the pipeline case, usually multiple bits are resolved in one step. Therefore, they are faster than the integration but slower than the flash types. In addition, there are also time-interleaved ADC arrays and noise-shaping oversampled delta sigma ADCs. This plot here shows the sample rate and resolution trade-off among most common ADC types. In the last 10 to 20 years, the SAR, oversampling, and time-interleaved ADCs are very popular. The DAC architectures in general can be divided into the Nyquist and the oversampling types as well. We will focus on the Nyquist DAC architectures shown in this table according to the circuit elements used, resistive, capacitive, current steering, and the way they are arranged in an array, binary weighted, unit element, or segmented. For example, the Archwire DAC employs resistors of two values, R and 2R, arranged in a ladder to provide binary weighted branch current divisions. Capacitor DACs, often called the charge redistribution type, can be arranged in either of the three topologies. Current steering DACs usually operate at high speeds. Lastly, two interesting facts about DACs are listed here. First, every ADC must have a DAC built in. Second, while DACs are conceptually straightforward, they are usually difficult to implement at very high speeds. Next, let's turn our attention to the measurement techniques of data converters. Generally, there are two ways to measure data converter performance. A direct transfer function measurement is usually slow and only suitable to obtain static nonlinearities of converters, such as the differential nonlinearity and the integral nonlinearity, the DNL and ANL. In dynamic measurements, a highly accurate sine wave, either analog or digital, is fed to the converter, and the measured output is analyzed to determine what degradation of signal quality was introduced by the converter. These measures can be realized in either frequency or time domain. Generally speaking, dynamic measurements are preferred to analyze high-frequency error syndromes of data converters. Now let's examine the static measurements of DNL and ANL. Like any analog circuits, Data converters exhibit transfer function non-idealities such as offset, gain error, and nonlinearity. What's unique about converters is that they often display segmentation errors, manifested as a sudden jump or setback within a small input range such as 1 LSB. In contrast, continuous time analog circuits do not behave this way. Their nonlinearities are usually continuous and smooth. This leads us to care not only the smooth or global nonlinearity, but also local, potentially fast varying transitions in the transfer function. The former is called the integral nonlinearity, and the latter called the differential nonlinearity. The DNL basically measures the deviation of one transition step from its ideal value of 1 LSB, while the INL measures the deviation of the actual transfer function from its ideal counterpart. This reminds us of how a piecewise approximation can be used to calculate the area underneath a nonlinear curve in calculus. Similarly, we conclude that INL is essentially the cumulative sum of DNL. An example INL and DNL plot for a 10-bit DAC is shown in this plot. Note that INL and DNL are always plotted against the digital code, no matter for a DAC or an ADC. In practice, however, there may be offset and gain errors in the transfer function. So what is usually done in measurements is to best fit a straight line through the measured transfer function first, then stretch the line to its ideal position, dragging the actual transfer function with it. This procedure essentially corrects the offset and gain errors. DNL and INL can then be calculated from the stretched curve. There is a function called dtrend in MATLAB, which does exactly what is described here, so we don't have to reinvent the wheels. Since the fitting always removes the mean from the curve, the average value of the INL measured this way must always be 0. Lastly, for DACs, since the measurement always starts from the digital domain, even when the negative segmentation error causes a non-monotonic transfer function, the actual DNL can always be measured faithfully, no matter how large or small the error is. However, this is not true in the ADC case. For example, suppose the code 101 is missing with a transition step size of 0. This code therefore has a DNL value of -1. The question is, can anything be worse than the missing code? As the input scans from 0 to full scale monotonically, a code transition can be up or down, but it can never go left or right. Therefore, a missing code is the worst scenario, and the minimum value of DNL is -1. Additionally, calculating DNLs for non-monotonic code transitions can be even more troublesome. In the figure shown here, code 010 shows two disjoint transition steps in points 1 and 2 due to a non-monotonic segmentation error. Simply lumping them together leads to obviously ambiguous results. Therefore, when measuring DNL and INL of ADCs, special attention must be paid to missing code and non-monotonic code. The actual procedure is similar to that of the DAC measurement. We first connect the midpoint of all transition steps, then fit a line through the curve, detrend it, and then calculate INL and DNL. If you're picky, you may be concerned about the small offset around half LSB introduced in this procedure. But no worries, it simply vanishes in a fully differential implementation, such as the one we saw when studying the quantization noise. Lastly, a direct measurement of ADC transfer function usually dictates a high-resolution DAC to produce a highly linear ramp signal. The DAC must have a higher resolution and linearity than the ADC under test. A simpler procedure can be used to measure INL and DNL directly without obtaining the ADC transfer function first. This is done by applying a linear ramp to the ADC and recording the number of hits of each code digitally. Because the linear ramp is uniformly distributed across the ADC input range, the number of hits of a particular code must be proportional to its step size, which essentially represents the DNL. Of course, in such a measurement, the true LSB size is unknown, so the mean of the histogram is used instead of the true mean. This DNL-NL measurement is called the code density test, or CDT. A missing code or zero count is usually not a problem in this test, but a non-monotonic code presents quite a challenge, because disjoint transition steps corresponding to the same code are simply lumped together in the histogram. For this reason, DNL and RNL results obtained through CDT test can be misleading. Lastly, since linear ramps are difficult to generate, bandpass filtered sine waves are often used. However, sine waves are not linear. They tend to linger more at the peak and bottom than the zero crossings, resulting in a bow-shaped histogram. Such shaping can be pre-calculated and corrected. RNL and DNL are static linearity measurements of the converter transfer function. Alternatively, a real-time signal quality measurement can be done to gauge the conversion error, including all noise and distortions, static or dynamic. This measurement is usually preferred over DNL and RNL, especially at high signal frequencies. To begin with this procedure, let's examine the spectrum of a quantized signal. Earlier we argued that if the signal is large and busy, quantization error can be considered as white noise. This figure shows the quantized spectrum of a sine wave at 10-bit level. The quantization noise indeed behaves like white noise. If we remove the signal bin in the spectrum, sum of all the other bins, we can estimate the quantization noise power. In this particular example, an SQNR of nearly 62 dB was obtained. For sinusoidal signal, an effective number of bits of ENOP can be defined using this equation. The ENOP calculated was 9.995 bits in this example. Strictly speaking, the power of a random process like noise must be calculated using its autocorrelation function. Therefore, a direct FFT calculation is only approximate, which explains the deviations of SQNR and ENOP from their ideal values. But since this method is simple and fast, it is widely used in practice. Lastly, when performing such a test, we must remember that, first, FFT requires a power of 2 number of samples for computing. And secondly, the sample rate and the signal frequency better be coprime. And third, the samples better include an integer number of input sine wave cycles. This slide shows what happens when the second condition is not satisfied. In the left figure, the sample rate is 8,192 and the input frequency is 256. Since the choice of input frequency leads to periodically repeating samples, the quantization error is also periodic, manifested as harmonics instead of noise. A more ridiculous choice of Fin is 2048, exactly a quarter of the sample rate. The right figure shows that no quantization noise can be observed. So, where are they? Well, they're actually all hiding behind the signal bin. About the third condition, a problem called spectrum leakage occurs when the quantized samples do not include exactly integer number of cycles. A typical such case is shown in the left figure, where the input frequency has been slightly offset. It is clearly difficult to separate the signal from the noise in this spectrum. Fortunately, a numerical method called windowing comes to rescue. The right figure shows the exact same FFT but with a Blackman window applied to the sample sequence first. Many window flavors are readily available in MATLAB. In practice, conversion errors also include distortions and other noise. This figure shows a more realistic quantized spectrum with clearly visible harmonics. If the signal bin is removed, the sum of all other bins in power would include all noise and distortions. We can define a signal to noise plus distortion ratio, or SNDR, and correspondingly the ENOP, which is given in this equation. Again, for sinusoidal inputs. Interestingly, we never lose a harmonic in a digitized spectrum. All harmonics can be traced by properly aliasing them back to the first Nyquist band. Two examples are shown here. We can also calculate the total harmonic distortion and spurious free dynamic range, which is the distance in dB between the signal and the largest spur in the spectrum, which may or may not be harmonically related to the input. In wireless systems, the average noise amplitude spectral density, or NSD, is often of interest. It has a dimension of volt per root hertz. Lastly, when windowing is applied, or in a real-world measurement, the input or the clock generator may show large phase noise. The signal and harmonic beams in the spectrum may spread out. While SFDR measurement is not affected by this, all other spectral measurements become quite difficult. In this case, a time domain technique can be used instead by fitting the sample sequence to an ideal sine wave of the same frequency, amplitude, and phase. The difference between the fitted samples and actual ones then gives an error sequence that includes all conversion errors. SNVR and ENOB can then be calculated. Unfortunately, it is rather difficult to determine other performance metrics such as the SFDR without a spectrum. Also, in a real experiment, the exact frequency, amplitude, and phase of the input sine wave are also not known. Therefore, some initial guess is necessary. Now let's look at Nyquist ADC architectures, including flash, SAR, and pipeline. In a flash ADC, usually a unit element resistive ladder is employed to obtain the reference steps of all conversion steps. Equal number of comparators trail the reference ladder to compare each reference step to the input voltage. Therefore, no matter where the input is located between 0 and the full scale, two comparators were immediately located with one comparison. The massive parallelism employed in the flash ADC makes it extremely fast. However, the speed advantage also entails its primary disadvantage, complexity, which is exponentially dependent on the resolution. Therefore, flash is rarely used in applications requiring more than 6 to 8 bits. This slide reveals some details of the flash operation. Suppose the input lies where the green arrow is. All comparators above this level will resolve to 0, while those below it all resolve to 1. Such a digital code is called the thermometer code, as the boundary of 0 and 1s moves up and down with the input, just like a thermometer when temperature changes. Training the comparators, a bank of logic gates can be deployed to detect the 0-1 boundary and produce a one-hot code to select the one row of a prearranged ROM encoder, producing a final binary output. The two-step encoding process is called the thermometer to binary encoder. We see that the comparators are critical decision-making devices. In a flash ADC, they are required to make fine decisions at the reference steps are usually closely spaced, especially when the supply voltage is low. Unfortunately, comparators sometimes make errors. This diagram shows that one comparator, close but not in the immediate vicinity of the input, misfired, resulting in a bubble error in the thermometer code. If nothing has been done to anticipate this error, two hot codes will be produced and the final binary output is garbled. Techniques such as 3-input boundary detectors, majority voting, and gray coding can be deployed to combat the bubble errors in flash ADCs. Earlier, we talked about quantization being related to division. Let's see how a binary division can be performed by a human. Suppose we want to quantize an input 735 out of a full scale of 1000 to 3 bits. We first compare the input to half the full scale, 500 in this case. Since 735 is greater than 500, the first quotient of 1 is obtained. This is the MSB. We then subtract 500 from 735 to produce a remainder or residue, 235 in this case, and then compares it with the quarter of the full scale, 250. The process then iterates until all 3 bits are resolved. Note that the comparison threshold is halved each time the process is iterated, which is therefore called the binary search. A binary search is exactly the conversion principle employed by a SAR ADC. There are mainly 3 functional units in a SAR: a comparator, a DAC, and some digital logic. The DAC is responsible to produce the successive threshold voltages during the binary search process. The comparator makes a 1 or 0 decision by comparing the input to the DAC voltages. And eventually, the digital logic records the serial decision bits in the register. The conversion process is iterative, and each time it loops around, 1 bit is resolved. Altogether, a minimum of n cycles are required for an n-bit resolution. This and the next 2 slides animate the first 3-bit cycles in a SAR ADC. There is a fine difference in this diagram about the comparator. It actually compares the difference between the input and the DAC values to a constant 0, which makes it a simple zero crossing detector. There is another way to perform division. When a residue is obtained in a bit cycle, one can double the residue such that it can be compared to a constant threshold, in this case 500, throughout the binary search process. In circuits, doubling the residue is to amplify it by a gain of 2. With the residue amplification, the n-bit SAR DAC is obviated, and the comparator threshold is kept constant. The resulting conversion architecture of the modified binary search algorithm is called algorithmic or cyclic type, shown in this diagram. Here the full resolution DAC is reduced to 1 bit. An amplifier is added to obtain a 2x gain of the residue, and the comparator always compares the amplified residue to the half full scale. The algorithmic ADC retains the same hardware efficiency as the SAR. The conversion throughput is also similar due to the iterative bit cycles. Lastly, the ideal residue transfer function, which is constant throughout the bit cycles, is given by the equation and plotted in this figure. It has 2 linear segments separated by the comparator threshold VFS over 2. And each segment has a slope of 2, ideally. The looped bit cycles of the algorithmic ADC can be unrolled into multiple conversion stages, with dedicated circuits responsible for each cycle. Once implemented this way, the stages can be naturally pipelined to significantly improve the conversion throughput. This architecture is called the pipeline ADC. If each stage takes 1 clock cycle to finish its job, the throughput can be maximally equal to the sample rate. Since the stages usually overlap their operations to amplify and sample the residues, similar to leapfrog, the overall latency is k over 2, where k is the total number of conversion stages. Power savings is also possible if later stages are tapered due to the cumulative residue gain along the pipeline. The optimal per stage resolution is usually around 3 to 4 bits. In the next section, we will look at the design trade-offs between the 3 popular DAC topologies: the binary weighted, the unit element, and the segmented approaches. The binary weighted structure is probably the most straightforward, in which a binary array of elements, directly controlled by the digital bits, produces a corresponding binary array of voltage, current, or charge quantities to be summed together to produce a final output. In this diagram, a binary capacitor array ranging from 8 unit capacitance to 1 unit is shown to sample the reference voltages VR or 0 and transfer the acquired charges to a common capacitor, the 16 unit capacitor, with the help of a feedback amplifier. Assuming a large loop gain, the feedback establishes a virtual ground, Vx, on which the charge transfer and summation occurs with high precision. We can visualize this accuracy by adding a parasitic capacitor Cp at the summing node, possibly derived from the bottom plates of the capacitors, the input of the amplifier, or the switches. Once the amplifier settles in phi 2, the virtual ground will return to nearly zero potential it started out with in phi 1. Therefore, Cp cannot transfer or receive any charge during the process, which is confirmed by the output voltage expression obtained using the charge conservation law. If the amplifier gain is very large, this equation essentially reduces to the ideal deck function. The binary weighted structure is very efficient. The digital bits are routed directly to the switches, controlling the array elements without additional decoding logic. While efficient, this architecture can suffer from a large DNL error at the MSB transitions. In the 4-bit charge array distribution example, this happens at the code transition from 0111 to code 1000. A simple calculation showed that a large mismatch error may occur because we're turning off half of the array while turning the other half on. Depending on the exact matching error between the two halves, a positive or negative DNL error will happen, as shown in the diagrams here. Alternatively, we can employ a unit element array of equal components to overcome the large DNL problem of the binary weighted architecture. In this case, a binary to thermometer decoder is required. A simple binary tree decoder is shown here in this diagram. With the help of the decoder, only one circuit element is turned on successively during each adjacent code transition, just like the behavior of the thermometer code. Therefore, the DNL performance is determined only by that one element. In the resistor DAC shown here, this is simply sigma R over R, the normalized standard deviation of the resistor matching accuracy. On the other hand, the RNL is cumulative over the entire array. Then this can be shown to be square root of 2 to the nth power divided by 2 times sigma, assuming independent matching between the resistors. In comparison, we also derived the statistical DNL and RNL performance of the binary weighted DAC. Without any surprise, the maximum DNL is as large as twice the maximum RNL at the mid-scale. The RNL performance between the two architectures are identical because RNL is cumulative no matter the circuit elements are arranged in a binary or unit element fashion. Lastly, because the unit element approach requires an exponentially complex switch matrix, it is rarely used in high-resolution applications. Another unit element DAC suitable for high-speed operations is the current steering type shown here. In each of the unit current steering cell, a differential pair switching a tail current source is employed. The binary to thermometer decoder sends the control bits and their complements to the differential pair switches, directing the tail currents to be steered to the positive or negative output, which usually terminates to a resistor, resulting in a final voltage output. At a gigasample per second plus switching speed, not only the matching of the tail current source is important, the timing control of the differential switches, as long as the clock phase synchronization across the entire array are equally critical. The latter often cause dynamic conversion errors of high-frequency outputs that are extremely difficult to get rid of. By this point, the trade-offs between the binary-weighted and unit element architectures are clear to us. A problem then arises in high-resolution applications, where neither one seems to be a good choice. To combine the advantage of the two, a segmented approach, or divide-and-conquer approach, is introduced. In this architecture, the overall n bits are first divided into two groups, an upper group of m bits and a lower group of l bits. For the upper m bits, a unit element topology is used for better performance, often laid out in a square matrix of equal number of rows and columns, while the lower L bits use an efficient binary control. Therefore, the total number of switching elements is 2 to the power of m plus L, which is way smaller than the straight unit element approach. Since the binary weighted lower segment simply fills the L bit gaps between the unit step transitions of the upper segments of m bits. As shown in this diagram, we conclude that the overall DNL performance will be limited by the binary weighted lower segments, which is only L bits, while the RNL, still cumulative over the entire array, remains constant. This architecture, therefore, is the preferred approach for high-speed and high-resolution applications. To compare the three DAC architectures covered so far, we summarize their statistical DNL and RNL results in this slide. An example of a 12-bit DAC with a unit element matching accuracy of 1%. The binary weighted approach yields the lowest number of switching elements, but the worst DNL. The unit element approach results in the best DNL performance, however, the highest number of switching elements. And lastly, the segmented approach of 8 plus 4 bits strikes a relatively good balance between the two performance matrices. We will look at a few circuit-level building blocks of data converters next. Converters are highly complex mixed-signal circuits, encompassing usually a large number of analog and digital circuit functions. We have looked at the DAC in the last section. In this section, we will cover the comparator and the sample and hold circuits. Due to the time limit of the tutorial, other building blocks such as residue amplifiers, reference and biasing circuits, clock distribution, and IOs, digital logics, and the last but not the least, input and the reference buffers, which are peripheral but tend to be power hungry, are skipped. ISSCC in the past has offered subject tutorials on some of these individual topics. Now let's look at the comparator design. Comparators are decision-making devices in data converters. They receive potentially fast-varying analog inputs and need to make quick and accurate decisions comparing the input to a reference voltage. An abstract ideal input-output characteristic of a comparator shows an infinite slope or small signal gain at the threshold. Obviously, such a large gain is difficult to procure in one step. Typically, comparators are made of a chain of analog and digital circuits, starting with one or more amplifiers called the preamps and terminating in digital latches and logics. In this arrangement, signal gain can be gradually picked up along the chain of processing. Additionally, since a comparator makes a black and white decision at the end, linearity is usually not necessary. Therefore, open-loop analog circuits are often employed. To help boost the final output to valid digital logic levels, positive feedback is usually also used in the latches. This slide shows a simple conventional comparator design in CMOS technology. It consists of two stages, a preamp and a latch. The preamp consists of an input differential pair and an active load to pass its output to the latch. The latch consists of a cross-coupled positive feedback NMOS pair and a crowbar reset switch showing blue. The comparator usually works under single-phase clock phi. When phi is high, the latch differential outputs are shorted by the crowbar, overriding the positive feedback. The whole circuit in this moment functions like an amplifier with a mild gain. A seed voltage will be established at the latch output when the clock signal goes low, in approximately half a clock cycle. When this happens, the crowbar is turned off and the positive feedback kicks in, starts the regeneration process. If the initial seed voltage is large enough or enough time is allowed, valid digital outputs will be produced at the end, indicating the input polarity at the beginning. While linearity is of no concern, the offset specs, especially for the preamp, can be quite stringent in, for example, flash converters. Also, the latch regeneration is usually a one-way drive, unless the input makes a large and sudden change during the regeneration. For this reason, the input voltage usually needs to be sampled before it is sent off to the comparator. We see latch regeneration is quite helpful to produce final digital outputs. However, even it is mostly digital, its timing budget is still quite stringent, especially in high-speed ADCs. The regeneration speed of a latch can be analyzed using the small signal equivalent circuit of the cross-coupled NMOS pair. Two simple equations solve to a right half plane pole at Gm over Cl, where Gm is the transconductance of the NMOS at the onset of regeneration and CL is the load capacitor. The right outplane pole is no surprising because of the positive feedback. Therefore, the latch usually starts regeneration with an exponentially rising transient. The time required to produce a 1 volt output level with different initial seed voltages is tabulated here. Obviously, a smaller seed leads to a longer regeneration time. Now let's include the preamplifier gain into account. Suppose it is 10. The seed voltage then can be input referred and again tabulated here. In this example, we see that the latch successfully regenerates within the allowed time for the first 3 input values. However, in the fourth case, when the input is only 10 microvolts away from the threshold, the latch output fails to reach valid logic levels. This problem is called comparator metastability. When this happens, training digital logics may interpret the latch output differently and arbitrarily, potentially leading to catastrophic conversion errors. For example, in asynchronous IADCs, the inception of the next bit cycle depends on the full regeneration of the current bit. When it fails, the bit cycle simply halts and no more bits will be resolved. The metastability error rate can be calculated by plotting the metastability regions around each decision threshold, such as shown in this plot. If all comparators are equal, this is equal to the metastability region of one comparator, say delta, divided by the LSB size. Metastability is a fundamental problem in waveform digitizers, especially those operating at very high speed. Besides carefully avoiding any disastrous consequences, usually little can be done, but to allow more time for comparator regeneration. Now let's revisit the simple two-stage comparator design and see how we can evolve it to a state-of-the-art topology. First, we note that the static tail current source is unnecessary, as the preamp is only active half of the time. We can replace it by a switch to make the preamp a dynamic one. And second, the NMOS pair in the latch does not help regenerate towards VDD, so we can add a PMOS pair similarly cross-coupled at the top. The two-stage cascade is not power efficient, as the latch still consumes quite some power during the reset phase. We can simply stack the two stages together to make the whole thing dynamic as shown here. The only problem is that the crowbar reset timing now conflicts with the preamp. So we replace the crowbar by PMOS transistors connected to VDD for a clean reset, which is now aligned with the preamp timing. The last remaining problem is that while the output nodes VL+, VL- can be clearly reset, the internal nodes 1 and 2 may get stuck to some unknown voltages as NMOS transistors cannot pass VDD while the input differential pair is off. This may lead to some memory effect that can cause hysteresis. Therefore, we add 2 more PMOS switches to clearly reset these 2 nodes. At the same time, the output is reset. And here we are, the final circuit, fully dynamic, compact, and operates on a single-phase clock. This is called the strong-arm comparator. Finally, we need to point out a large common mode kickback problem in this circuit. Nodes 1 and 2 both start off at VDD, but when regeneration goes on, one NMOS of the cross-coupled pair will remain on while the other turns off. If the differential pair is still on, then nodes 1 and 2 will both plunge towards 0 eventually. The large common mode swing on these 2 nodes therefore can capacitively couple back to the input nodes, which usually leads to large differential offset due to mismatch and undesirable disturbance to the preceding circuits. Let's look at the MOS samp and hold circuit next. Samp and hold mathematically can be visualized as a zeroth order hold function shown in this diagram, where an input signal is acquired instantaneously and held for the whole sample period of t. We understand that a zero acquisition time is not realistic. In practice, a track and hold function is more often used. The sample period is divided into 2 parts. One part is used to track the input and the other to hold the acquired sample for further processing. MOS technology is particularly suitable for implementing samp and hold functions because MOSFETs are natural switches. The circuit shown in this slide is called the top plate sampler. Here the signal is sampled and stored as charge on a capacitor, CS, which is periodically connected to the input source via a MOSFET switch. The on resistance of the MOSFET is not constant and depends on the input, as shown in this equation. Even when the CMOS switch is used, the switch resistance still depends on the input. In high-speed sample and holds, this often leads to a signal-dependent tracking bandwidth that causes dynamic distortions to the samples. The tracking bandwidth of the top plate sampler is the inverse of the RC time constant of the switch and the sampling capacitor, and can be derived as shown here. A wider bandwidth usually requires a larger switch, but a larger switch also leads to a larger clock feed-through and charge injection errors when it is turned off, degrading the sample and hold performance. Assuming that half of the channel charge ends up on the sampling cap, which is a grossly crude approximation, we can define a performance matrix for sample and hold as a ratio of the tracking bandwidth to the charge injection error. The larger this quantity, the better the performance. This matrix turns out to be inversely proportional to the square of the channel length of the switch transistor. Therefore, technology scaling helps sample and hold performance in general, as long as the leakage is not a problem. A closer examination of the top plate sampler operation also reveals that the exact time when the switch turns off, or the sampling moment, depends on the input. This usually leads to signal-dependent modulations of sampling times called aperture error. To mitigate this problem, a bottom plate sampler shown in this diagram is introduced, where two switches are employed, with the bottom plate of the capacitor facing the input side. The other side, node X, is connected to an AC ground during input tracking. If this switch is turned off slightly earlier than the input or bottom plate switch, the aperture timing and switch-induced errors are then set by the early switch, which is largely signal independent. Therefore, even the tracking bandwidth is degraded. The bottom plate sampler is still widely used in sample and hold circuits requiring higher precisions. For example, about 10 to 12 bits. Sampling clock jitter also impacts the aperture timing, as illustrated in this diagram. Since jitter is random, the induced aperture error is also random, manifested as noise. It usually matters more for high-frequency signals as the signal slope, or dV/dt, is larger. This problem has been analyzed in detail in reference 5, and the closed form result is quoted here. For sinusoidal input, we can then plot the resulting SNR due to clock jitter as shown in this figure. For example, a 100 MHz full-scale sine wave sampled with a clock jitter of 1 picosecond gives a maximum of 10-bit SNR, or approximately 62 dB. In addition to noise caused by aperture jitter, switch capacitor sample and hold circuits are also subject to thermal noise. Using a linear circuit approximation, the thermal noise of the switch can be integrated over the tracking bandwidth, resulting in the well-known KTRC noise. This noise is a function of the sampling capacitor size and temperature. At room temperature, the RMS noise is listed in this table for a few different capacitor sizes. It is a good practice to remember that a 1-puff capacitor results in a 64 microvolt RMS noise. When all noise sources and distortions are included, an SNDR of sample and hold can be defined, as shown in this equation. Lastly, let's study the clock bootstrapping circuit commonly used in MOS sample and holds. The idea is that, suppose a floating voltage source equal to the supply voltage is available, and we can switch that on and off to drive a MOS switch as shown here. We can then achieve a constant gate overdrive of the switch, which in turn leads to a constant on resistance and a constant tracking bandwidth to a first-order approximation. This clearly improves the sample and hold tracking performance. In addition, a single NMOS switch is sufficient when bootstrapped. There is no need to add a PMOS. The clock bootstrapper can be implemented by a charge pump, shown here, a capacitor, C, which essentially is a floating battery, charge to VDD, and some additional switches to turn on and off the battery to drive the switch, which is transistor M1 here. The principle of the bootstrapper is straightforward. However, since the highest voltage in the circuit can be twice the VDD, extra care must be taken to ensure the reliability of the circuit. We now switch gear to talk about a critical concept in data converters, the redundancy. It's hardly an exaggeration that no multi-step ADC works without redundancy. Let's first examine what happens when a comparator offset is present in the pipeline ADC. The residue transfer function of a 1-bit per stage architecture is plotted here. For example, the comparator threshold is set to the mid-scale VFS/2. The second stage is identical to the first stage. When everything is ideal, the cascade of the two stages resolve to 2 bits, and the ADC transfer function is shown to be ideal in this case. Now suppose the first comparator exhibits an offset. The 0-1 decision boundary of the MSB is slightly shifted to the right, and the residual voltage now extends to beyond the full scale, as indicated by the red curve. Since the second stage has no overrange capacity, the second bit is still resolved to 1 in the shaded region. When the 2 bits are assembled, an equal amount of offset is introduced to the transition between the codes 0-1 and 1-0. This analysis indicates that the ADC has a nearly zero tolerance to comparator offset. To resolve this problem, we can introduce 2 more comparators in the second stage, one placed at the full scale and the other at 0. In the case of a positive offset just discussed, the second bit will then resolve to 2 when the residue exceeds the full scale. This results in a redundant code of 0-2 in the shaded region. Since 0-2 is equal to 1-0 in the binary format, the notch in ADC transfer function due to offset is fixed. To understand how exactly redundancy works, we can take a closer look at the residue equation. Here, we inverted the relationship to express the input as a summation of the first decision bit and the residue voltage. Now look at the residue plot. In the shaded region of offset, the MSB is resolved to 0 instead of 1, so a -1 digital offset is introduced. But when this happens, the analog residue is also shifted, correspondingly by plus V4 scale. Exactly. Therefore, if the second stage can resolve the overrange residues, the negative digital offsets and the positive residue analog offset are exactly cancelled once the final digital codes are assembled, as shown in these equations. So in this case, the redundancy works by introducing complementary analog and digital errors to cancel each other in the presence of comparator offsets. To generalize this, we can consider the following hypothetical scenario. Here we use a differential 1-bit per stage residue transfer for better clarity. We know that as long as complementary analog and digital errors are introduced, the ADC is always error-free. So we can introduce a second comparator at 3/4 of the full scale, as indicated by the red curve. This leads to a new code 0.5 resolved. But at the same time, since the analog residue is shifted up by half full scale, the digital and analog errors introduced are totally complementary. The modified transfer curve works just as well as the original one. Also, because no out-of-range residue is introduced, there is no need to modify the second stage at all. Next, let's consider an opposite scenario, as shown in the left figure. Here, a new comparator is introduced at 1/4 of the full scale, leading to a symmetric argument as we just did in the 3/4 case. As a matter of fact, we can now shift the 2 comparator thresholds anywhere in between the 2 cases, and in any case, the ADC is still error-free. The optimal location of the 2 thresholds are shown in the figure at ± VR/4, resulting in a totally symmetric differential transfer curve. Now we can argue that when comparator offsets are present, these thresholds can shift left or right, but the ADC is always error-free as long as they do not cross each other. So the maximum offset tolerance is plus minus VR over 4 in this case, or a quarter of the full scale. This is the famous 1.5 bit per stage pipeline architecture. In computer science, this is also known as the SRT fast division algorithm. At this point, may I remind everyone that ADCs are dividers? The circuit implementation of the 1.5 bit per stage pipeline ADC is shown in this figure, including 2 capacitors, 2 comparators, 1 residue amplifier, and some digital logic. The residue equation is also shown here for completeness. The 1.5 bit per stage architecture can be generalized to an n.5 bit per stage architecture. A 2.5 bit example is shown in this slide. Here, 6 comparators are employed, and the residue curve is divided into 7 linear segments, each exhibiting an ideal slope of 4. The ideal residue equation and the transfer function are also shown. It is interesting to note that in the ideal n.5 bit per stage residue curve, half of the internal residue dynamic range is reserved as redundancy to tolerate comparator offsets. One can argue that a residue amplifier offset can be absorbed by the redundancy in a similar fashion. A more realistic residue plot with random comparator offsets is also plotted here in red for appreciation of the internal architectural redundancy. Now we conclude the pipeline discussion by highlighting the redundant bit assembly procedure. Take the 1.5 bit case as an example. Each pipeline stage contributes 2 redundant bits. They are overlapped and summed up in the final assembly as illustrated in this table. We emphasize that before summation takes place, these decision bits, collected in a vector format called the decision vector, contain redundancy. Once the summation is done, an n-bit scalar is obtained and the redundancy is removed. We also recognize that the overlap and summation procedure as a weighted sum operation on the decision vector. The ideal weights, in this case, are 1/2, 1/4, 1/8, and so on and so forth. We now turn our attention to the SAR ADC and study how redundancy works in this architecture. Earlier we talked about the bit cycles. In an ideal binary search process, no overlap exists between the abutting but disjoint 2 halves of the search ranges during a bit cycle, as shown in this 4-bit example. The search ranges are exactly halved each time we move into the next bit cycle. The ratios between the successive ranges are exactly 2. We call this the binary or radix 2 search. In contrast, a redundant SAR ADC employs a sub-binary search process in which the search ranges are overlapped in a bit cycle, as indicated by the purple bars in this figure. Due to the overlap, the net resolution is reduced and a 5th search cycle is necessary. In this example, the ratios between the successive search ranges are highlighted at the top, which are all less than 2. We also call this the subradix 2 search. To understand how redundancy works, we first look at how a binary search can fail when circuit errors are present. Suppose the input is located near the code 1011. In the ideal binary search process, 4 decision thresholds 0, 1/2, 1/4, 3/8 will be successfully selected. When no circuit error is present, the comparator will resolve to 4 bits 1, 0, 1, 1 successively. During the second bit cycle, we note that the input and the comparator threshold 1/2 come very close to each other. Suppose the comparator made a mistake and resolved the second bit to 1 instead of 0. The conversion process will then take a different path, ending at the code 1100, which is obviously wrong. While it sounds like a small error in this 4-bit example, the error can be quite large if the ADC resolution is much higher. The magic about sub-binary search is that an earlier decision error can be recovered later in the process. Using the 5-bit sub-binary example, we can see that ideally the decision path is 11001, which points to the correct binary code 1011. Obviously, a lookup table here is necessary in this case to encode the non-binary bits to the binary ones. Now suppose the same bit decision error occurred during the second bit cycle, and the conversion takes an alternative path shown in red, which interestingly ended up with the same correct binary code, 1011. So how did this work? A closer look at second bit cycle when the comparator flop happened shows that even the bit decision was wrong and we ended up on the other side of the search range. Because the error is within the purple redundancy range, the search process will reconverge to the correct decision eventually. The subbinary redundancy seems arbitrary in the previous example, which is actually true. Typically, the redundancy is tapered towards the end of the conversion process, which is indicated by the shorter and shorter purple bars toward the LSB. Such an arbitrary non-uniform radix is often implemented using a unit element DAC with the help of a digital lookup table for encoding, as reported in reference 8. Alternatively, a uniform radix can be employed by hard-coding the radix into the binary-weighted DAC elements, obviating the digital effort involved, as shown in reference 9. Lastly, redundant cycles can be inserted sporadically during the bit cycles to absorb earlier decision errors. In this case, the radices are either 2 or 1, which simplifies the layout of the SAR ADC. The last case was reported in reference 10. Take the uniform subradix to SAR ADC as example. In switch capacitor technology, the redundancy is hard-coded in adjacent capacitor ratios, which is slightly less than 2. Other than that, the SAR ADC is identical to a binary one. This approach aids the conversion speed in two folds. First, redundancy allows some amount of decision errors, which in turn relaxes the precision requirement of analog circuits during the conversion. Second, hard-coded radix in analog domain minimize the digital effort involved, which also improves the conversion throughput. Lastly, this architecture is particularly suitable for high-resolution SAR ADCs that dictates radix calibration, as the exact radices of the DAC elements are nonetheless not precisely known due to mismatch. Lastly, we also highlight the bit assembly procedure in redundant SAR ADCs, using the uniform radix case as example. Suppose the conversion was successful and the correct decision path was identified. Then the last DAC output must be the best approximation of the input. Due to charge conservation, each decision bit multiplied by the exact value of the corresponding capacitor and the reference voltage must sum up to the total charge on the DAC, which in turn must be equal to the initial charge acquired by the DAC during sampling. This calculation essentially renders us an accurate expression of the quantized input as shown here. The WJs here are called the bit weights. An example of a uniform radix 1.8 case is shown in the table. Again, we highlight the distinctions between the decision vector and the scalar decision. Redundancy is contained in the vector but removed in the scalar. With redundancy covered, let's take a look at digital calibration of multi-step ADCs. CMOS technology scaling presents a great opportunity to improve analog circuit performance using digital means. Many analog errors, such as offset, gain error, and even nonlinearity, can be digitally corrected. Digital calibration is a gift of Moore's law and is recognized as a major trend in data converter design in the last 2 decades. In a typical multi-stage or multi-step ADC, major conversion errors often manifest as segmentation glitches, such as missing codes, non-monotonic codes, and missing decision levels, shown in this figure. The former two syndromes often show up as vertical jumps or setbacks at major code transitions, while missing decision levels are flat parts of the transfer curve where multiple input analog values gain into a single digital code. Theoretically speaking, as long as the mapping from analog input to digital code is unique, the conversion error involved is digitally correctable, because one can argue that theoretically a lookup table, no matter how big, can always be constructed to remove the error. Therefore, missing codes are obviously correctable, whereas missing decision levels are not. Non-monotonic codes, however, require some examination. In the figure shown here, two analog values, V1 and V2, map to the same scalar output. The rule of thumb seems to indicate that this is not correctable, but a closer look shows that even V1 and V2 map to the same scalar output, the decision vectors are different, as they belong to distinct segments of transfer curves. Therefore, non-monotonic codes are actually correctable. In contrast, the missing decision levels are also plotted here for comparison. Since the decision scalar and vector are both identical between V3 and V4, therefore, missing decision levels are not correctable. In pipeline ADCs, various static and dynamic errors exist. Some of these errors are listed here. Usually, static errors are easier and more reliable to correct than dynamic ones. The residue transfer equation, embodying most dominant static nonlinearities, such as capacitor mismatch, static sample and hold distortion, finite gain error, and nonlinearity of residue amplifier, are usually the starting point of a digital calibration. In a 1.5-bit architecture, capacitor mismatch and finite residue gain can be shown to result in segmental jumps and major code transitions, causing either missing or non-monotonic code. A typical transfer curve with missing codes is shown here for illustration. A digital correction in this case is obviously feasible. If the amplifier nonlinearity is also included, the transfer curve can display curvatures like the one plotted here. While slightly more complicated, these static nonlinearities are certainly correctable. Some earlier works on digital correction of certain dynamic errors in pipeline ADCs are reported in reference 25 and reference 26. These calibrations can be generalized to n.5-bit architectures. When calibrating a complete multi-stage pipeline, the stage decision vectors can be reversely pipelined in the digital domain from LSB to MSB to successively remove the conversion errors in each stage, especially when they are nonlinear. Mathematically, we can invert the residue transfer equation to obtain a stage-by-stage error correction equation, as shown here. This equation usually takes two forms, a linear and a nonlinear one. The nonlinear formulation often involves a low-order power series expansion of circuit nonlinearities, such as the signal-dependent gain of the residue amplifier and static sample hold distortions. Therefore, an important task of digital calibration is to accurately and efficiently identify these model coefficients. In SAR ADCs, DAC mismatch errors lead to radix and bit weight inaccuracies, and are usually the dominant static errors. A digital calibration essentially boils down to identifying the exact values of the WJs here before the final bit assembly is carried out. We will now see how redundancy can be exploited to facilitate a few popular digital background calibrations in SAR and pipeline ADCs. In the first example, we study the background residue gain calibration using a technique called DAC dithering. In the typical pipeline stage shown here, we know that half of the internal dynamic range is reserved as redundancy. So an opportunity arises in which a pseudorandom bit sequence T is injected to the comparator code before it is routed to the DAC. To avoid saturating the residue, care must be taken to ensure that the injected signal is small enough. This can be done by downscaling the injection element for T by a factor of 4 relative to the LSB size of the DAC. Therefore, the calibration signal only occupies half of the internal redundancy, as indicated by the shaded regions in the inset. Ideally, once the injected signal travels through the whole pipeline and arrives back at the calibration point, it can then be removed by properly aligning any latency in the code. However, when there is a residue gain error, the return signal T won't match its original value exactly. Therefore, even after removal, the back-end digital code D2 hat will still contain some residual part of T. A digital correlation of the two can then be used to reveal such a problem. It follows that an adaptive algorithm can be devised to correct the gain error until the correlation completely drops out. We emphasize that the whole procedure usually results in zero noticeable difference to a user, as it is executed all in the background while the ADC is converting normally. Another method of calibration employing a different technique called comparator dithering is shown here. The random signal T is injected to the input of the sub-ADC instead of its output. We know from the redundancy study that such injection can be considered as random comparator offsets and naturally tolerated by the redundancy. A slight advantage of this method is that T does not need to be removed from the digital output, as it simply bumps the conversion randomly between two redundant paths. When everything is ideal, the two end up with indistinguishable differences. But in the case there is a gain error, the two will differ. Therefore, a digital correlation can be similarly deployed to adaptively correct the conversion results. In a subbinary SAR ADC, radix or bit weight inaccuracies can also be background calibrated. Let's revisit the redundant search range in the typical bit cycle, the region highlighted in purple in the figure. We first zoom in and rotate the diagram by 90 degrees. Now the two boundaries of the overlap, V1 and V2, indicate the endpoints of the two overlapped search ranges. Depending on the actual design, the comparison threshold typically is chosen at either V1 or V2, but not both. As a result, the ADC transfer curve follows either the solid red or the dashed blue curve in this region, but not both. However, we can inject a small PRBS into the SAR DAC and artificially shift the conversion curve slightly. The conversion will then be forced to travel to redundant paths randomly, depending on the value of the injection. A similar adaptation can be devised to identify the bit weights until the two curves collide into each other. In reference 28, a small DAC capacitor is used for the random signal injection. At this point, you probably are quite excited by the fact of background calibration, but I like to pour some cold water to the fire. There are no artifacts associated with the background calibrations. For example, the vis-a-vis rule. What you see is what you get. A background calibration usually cannot figure out errors where the input signal does not travel to. Therefore, the results obtained often depends on the input statistics, especially in the nonlinear calibration. Additionally, there's a PVT rule. As many analog impairments are dependent on process voltage and temperature, the latter two are particularly problematic if the supply voltage and temperature cannot be maintained relatively constant. A digital correlation process usually takes a long time to converge, especially when the injection is tiny relative to the large input signal. So the tracking time of the digital algorithm could be a problem. A picture is better than 1,000 words. I'm sure you may laugh here, but I assure you, this was the actual sticker I found on my modem after the technician left. Now this takes us to the last topic of this tutorial, the figure merits of analog to digital converters. We will look at the popular Warden and Schreier figure merits first, then introduce a new one called the alpha form. Data converters are precision mixed signal circuits. They invariably are subject to power, speed, and precision trade-offs like any other analog circuits. Typically, power consumption of analog circuits is proportional to the circuit bandwidth or speed, while signal accuracy is inversely proportional to thermal noise or component mismatch errors. Noise and matching are two fundamental limits of analog performance. Both scale inversely proportional to the square root of the circuit size, and therefore power. For example, we know that circuit complexity of a flash ADC is naturally exponentially dependent on its resolution. In the low resolution case, the quantization noise is probably dominant over thermal noise and component mismatch. So we conclude that its power and area consumptions are proportional to 2 to the power of n, or 2 to the power of E knob, where n is the nominal resolution and E knob is the effective resolution. On the other hand, when it comes to high resolutions, where thermal noise and mismatch tend to limit the design trade-offs, we conclude that the power and area of ADCs would be proportional to 4 to the power ENOP. This observation actually turns out to be true for many analog circuits. The Walden form essentially measures the exponential dependence of an ADC complexity on its resolution, defined by the total power consumption normalized to the sample rate and 2 to the power ENOP. It inherently assumes that the design is complexity limited, not noise or matching limited. In contrast, the Schreier form, by its definition, attempts to measure the SNDR, which we will show shortly is proportional to the 4 to the power of ENOP. We distinguish these two scenarios as A versus B. Interestingly, the definitions entail that the dimension of the Walden form is joule per conversion step, whereas the Schreier form has a dimension of dB, seemingly implying that the former measures the energy efficiency of the converter, while the latter cares more about performance. The two forms are often plotted against the sample rate or resolution, but not both at the same time, because we'll need a 3D plot to do that. This becomes a little tedious as we need to look at multiple plots before a comprehensive impression about the work can be developed. Shown here are two typical such plots I found on Boris Merman's ADC performance survey, available online. So the question is, are there any easier way of doing this? Before we come to a solution, let's examine a little bit more on the similarity between the Walden and Schreier forms. Some manipulation is needed in the Schreier case. But based on the definitions of SNDR and ENOP, we eventually arrive at the same conclusion as being pointed out 2 slides ago. The Walden form measures the design complexity, where Schreier form assumes noise or matching limited designs. One is proportional to, or maybe inversely proportional to, 2 to the power ENOP, and the other one is proportional to 4 to the power of ENOP. This is a striking resemblance. If we call the base of these exponentials alpha, then the only difference between the two forms is that one uses the base of 2, while the other uses the base of 4. At this point, the analysis motivates us to define a common form, which is similar to the Walden form, but the base of the ENOP exponential is alpha, which varies from 2 to 4. At the same time, we also define a new quantity called performance, which is a product of the bandwidth and the ENOP exponential. This means performance measures speed and precision of converters at the same time. Furthermore, if we multiply the efficiency and the performance together, according to this simple calculation, we get the power back. This indicates that efficiency and performance are inversely proportional to each other when the power is kept constant. In mathematics, this trade-off is often called the power law or alpha law. Therefore, we call this new form the alpha form. The alpha form can be used to plot the performance of an ADC versus its efficiency in a log-log plot like this. Therefore, data points of high performance are usually at the top, while those of high efficiency are on the left. And the best designs with both matrices outstanding should locate at the top left corner. In addition, the power of these ADCs can also be plotted as a family of these constant power hyperbolas. I call this plot the performance efficiency chart, or simply the PE chart. This figure shows all ISSCC and VLSI data converter publications from 1997 to present using the alpha form. The circles are ISSCC data points and triangles are VLSI. The red dots are papers from this year's ISSCC. The power, efficiency, performance trade-offs are all captured in this single plot. Here an alpha value of 3 is assumed. We're naturally curious about how sensitive the alpha form may depend on the value of alpha. So here we plotted the same data again by assuming 3 values of alpha. From left to right, alpha equals 2, 3, and 4. The middle plot is the same one we just saw. The left plot corresponds to the Warden form, whereas the right plot corresponds to the Schreier form. It seems that data points are more scattered when a larger alpha is used, which makes sense, as alpha is the base of the exponential function. A larger alpha probably implies a higher sensitivity to the ENOP, or resolution of an ADC. Additionally, none of the plot seems to significantly change the relative location of these data points, indicating that the fairness of comparison is probably not compromised by a specific choice of alpha. It is also interesting to look at the evolution of data points over the last 25 years. This is the pre-2000 data. Moving to 2010, both performance and efficiency of these ADCs are clearly improving. Now at the last 10 years, it seems efficiency still got quite improved, but unfortunately, the performance did not. Lastly, in this plot, the academic and industry works are clearly separated into two groups. The purples are industry works, and the greens are university works. I always found it amusing to look at this plot. In the last 25 years, clearly, most of our industry colleagues care very much about performance, regardless of power consumption, whereas our academic colleagues are more concerned about efficiency. Oh, well, maybe both. Before I conclude this tutorial, I'd like to remind everyone some nice data converter papers to see at ISSCC this year. We have two data converter sessions, Session 10 and Session 17, both on Tuesday. In the morning, papers 10.1 and 10.2 are high-speed pipeline ADCs, and paper 10.4 is a high-resolution two-step SAR ADC. In the afternoon, paper 17.3 describe the high-speed RF DAC, and papers 17.4 and 17.6 are both time-interleaved SAR ADCs with extensive digital calibration. And lastly, paper 17.8 shows a high-speed ADC using time domain techniques. All right, that's all, folks, and thank you for your attention.